In this video, we are going to explore and model exponential growth and decay. We're going to use Newton's law of cooling. We're going to use logistic growth models. We're going to choose the appropriate model based on the data. Then we're going to express an exponential model of base E. So we're going to start out with some problems that we would have seen at the beginning of our chapter 4 when we started talking about exponential functions. And we know that exponential functions f of x will have the form of ab to the x. That means I'm going to use this ordered pair first and write this as 6 is equal to ab to the negative 2. I'm going to use a second order pair to get 6, not 6, I already used 6, how about 3? 1 is equal to ab to the third. Now I'm going to use both of these equations and solve for a, and then after I solve for a, I'm going to put it into the other equation, and when you get done, you're going to get a function of f of x is equal to 6 raised to the 7/5, that's your a value, and then you're going to have 1 over 6 raised to the x divided by 5. And that is your function when you get done. You're going to do something similar here. You're going to have the first ordered pairs, which is going to be 2000 is equal to ab to the 0. That's nice because we know what a is right away. And then the second ordered pair, you're going to have 20 is equal to ab squared. And when you get done, you should end up with f of x is equal to 2000, 1 over 10 raised to the x, or 0.1 to the x. We are going to be looking at population growth to start out with. There are some times in which the population growth will cap out, like it can't get any bigger because of resources. So as an example, fish in a pond. You can only have so many fish in that pond, and then the population will grow no further. When this happens, we call it a logistic function, a logistic growth function, and it's modeled in this way, where I have p of t is equal to a plus 1 over b e to the negative kt. We call this a logistic growth function, and it has a limiting value. So in other words, as t gets really large here, so as t goes to infinity, that the function itself will approach the line y is equal to a. And this is the horizontal asymptote of the graph, and it won't grow any further than that. So here is an example. We call this a carrying capacity. So again, in biology, an example would be the fish in a pond, and also bacteria. You can only have so much bacteria in a petri dish, and then it can grow no further. So as an example here, this would be the initial population. Notice how the initial population is c over 1 plus a. This is the point of inflection, and we're actually going to explore this in calculus. So, but here's how you would find the point of inflection. It would be the natural log of a over b, comma, c over 2. So this is the point of the maximum growth. So it's always growing, but here it's growing quicker to this point of inflection, and then the growth starts to slow down. And then here is the function and the carrying capacity. This is the most that the population can grow to because of resources. So the logistic growth model is this, where c is over 1 plus a is the initial value, c is the carrying capacity, and b is a constant determined by the rate of growth. So let's go through an example. We have a town whose population is 35,000. A disease creates an epidemic. The following number of n infected days after the disease has begun as given by this function. Now, at most, you're going to get 35,000 people, right? At most, you're going to get 35,000 people. So that's where that 35,000 goes, because you can't get any more than 35,000 people sick in a town of 35,000 people. If we want to know how many people were initially infected, I'm going to put in my calculator n of 0 into this function, so 35,000, which is 1 plus 19.9 e to the 0. Now, this is my C, my carrying capacity, over 1 plus A, because e to the 0 is 1. So I put that in my calculator, and I end up with, you all should put in your calculator as well, I end up with 1674.6. So 1674.6. Now, because these are people, we can't have 0.6 of a person, so we're going to round up to 1675 people. 1,675 people were initially infected. Now I'd like to know what happens after 2 days, 5 days, 8 days, 12 days, and 16. So N of 2 is equal to the 35,000, 1 plus the 19.9, e raised to the negative 0.6 multiplied by 2. Now I put this in my calculator, and of course we're always going to round up. I get 5,004.4, well, 0.5. So I'm going to say 5,005 people. I'm going to do the same thing for 5 days, 8 days, 12 days, and then 16 days later. So after 5 days, I end up with 17,000, I'm going to round up, 17,582. So that's a lot in 5 days. That's pretty infectious. It's about half, almost half. Well, that's a little, almost half. After 8 days, super infectious, I get 30,075. After 12 days, I'm going to get 34,488. Now, after 16 days, a little over 2 weeks after the outbreak happened, I'm going to end up with 34,953 people are currently infected. Now, will I ever reach 35,000? The answer is no. You will never actually reach the carrying capacity for many reasons. Now, mathematically, you just won't because it's a horizontal asymptote. But in real life, the reason is that some people will never leave their house. Like, they just don't leave their house. Or some people are going to be naturally immune to whatever infection is going around. So just because you have 35,000 people, that doesn't mean everyone's going to get infected. Here is Newton's law of cooling. Newton's law of cooling is T of T. A, which is the difference between the initial temperature and the object of the surrounding temperature. E raised to the KT, where K is a constant and it's a continuous rate of cooling. And T sub S, which is the surrounding air around it. So in a pot of boiling soup with an internal temperature of 100 Fahrenheit, it was taken off the stove and cooled to 69 degrees Fahrenheit room. After 15 minutes, the internal temperature of the soup was 95 degrees Fahrenheit. Use Newton's law of cooling to write a formula that models this situation. So what we're going to do is first do, since A is the difference between the initial, we're going to label everything. So A is equal to, in this case, it is 100 degrees because that's what the temperature of the boiling soup was, minus the temperature inside the room, which is 69. So we're going to get 31 degrees here. That's my A. My temperature of my room, T of S, is 69. And so, let me see. I have to figure out what my K is. So to figure out what my K is I'm going to say, okay, I know that T of T is equal to the 31 e to the KT, lowercase t, plus 69. We also know after 15 minutes, the internal temperature of the soup was 95. So the answer is 95 after 15 minutes. So we have 15K plus 69. Now what we're going to do is we are going to subtract 69 from both sides. So I'm going to get 26 is equal to 31e to the 15k. And divide both sides by 31, so I'm going to get 26 over 31 is equal to e to the 15k. Now I'm going to take the natural log of both sides. So the natural log of 26 over 31 is equal to, now remember, when I take the natural log of e raised to some power, it equals that power. So the right-hand side is just going to be 15k. So k is going to be equal to, I'm going to get my calculator out, and I'm going to do the natural log of 26 divided by 31, and I'm going to divide that answer by 15, and I end up with a k of negative 0.01173. Now when you find your k, you're going to want to write it out to several different, multiple decimal places. So my final answer, let me go back and put in my final answer. So I'm just going to erase this part. We have all of that. So I'm going to put in my final answer. T of t is equal to the 31e raised to the, I had negative, so negative 0.0. What did I have? A negative 0.01173t plus 69. So now if I want to know how long it's going to take to cool to 80 degrees, is I'm going to set this thing equal to 80, my equation I just built. 80 is equal to 31 e to the negative 0.01173t plus 69, and I'm going to solve for the t in this case. So I'm going to subtract 69 from both sides, and so I end up with 11. I'm going to divide by that 31, so 11 over 31 is equal to e raised to the negative 0.01173t. Take the natural log of both sides, and I'm going to divide by the coefficient. I'm going to get t is equal to 88. I ended up with 88.34 minutes. So I'll just do 88.4 minutes. So about 89 minutes before it's going to cool down. And round to the nearest what the temperature would be after 2.5 hours. So first of all, 2.5 hours. Since we are using t's in terms of minutes, we're going to have to turn this 2.5 hours into its equivalent minutes. So we take 2.5 and we multiply by 60, because there are 60 minutes in an hour. When we do 2.5 times the 60, we get 150 minutes. So now I'm just going to do t of 150 into this equation, 31e to the negative 0.01173 times 150 plus 69. And I'm going to end up with 74 degrees when I put that in my calculator. All right, so now we're going to talk about exponential growth or decay. We've actually talked about this previously, but the exponential growth or decay is all going to follow the same formula. And the formula is P naught, which is the initial population, e raised to the kt. Now, or you might see it as RT, or you might see it as something else, but whatever you have multiplication by the t or the variable is the growth rate or decay as a decimal from a percent. So if the k is positive, it's growing. If k is negative, so if your exponent is positive, you are growing. If your exponent is negative, it is decaying. And these are the two graphs. If you are told how long it takes to double or half-life, we can use these formulas. K being the rate times t being the time it takes to do a doubling or the time it takes to do a half-life. So if you are doing the doubling rate, you're going to have k, t is equal to the natural log of 2. So k is equal to the natural log of 2 over t, or t is going to be equal to the natural log of 2 over k. And the only difference between this, which is doubling, is instead of using ln of 2, if you want to find the half-life, you use 1/2, because it's half-life. So the decay rate or half-life, same kind of thing, except for if we're doing a decay rate and half-life, we usually use pi, or we use the natural log. Instead of 2, we use the natural log of 1/2. You can use a natural log of 2. You just got to remember that you need to put a negative on it. And you're like, what? Well, okay. So if we do in our calculators the natural log of 2, the natural log of 2 is 0.69315. And now I'm going to do the natural log of 0.5, or in other words, 1/2. And you ready for this? The natural log of 1/2 is negative 0.69315. So you can always use the natural log of 2 every time. Just remember to put a negative when it's a half-life. That's all. When it's in decay. All right, so we can also use this for when we're continuously compounding money. Same kind of thing, P naught E raised to the RT. Now we'll use an R instead of K. 6 of one, half a dozen of another. So let's take a look at these examples. We have a substance that has a half-life of 2.05 minutes. So they're telling me that capital T, they're telling me the capital T is the 2.045, which means I can find my decay rate is equal to the natural log of 1/2, or I can use 2, slap a negative on it. 2.045. I'm going to put that in my calculator. So I'm going to do the natural log, and then I'm going to divide by 2.045, and I get a K, and I'm going to run this out to about 5 decimal places. 0.3, negative 0.33895. If the initial amount of the substance was 132 grams, how many half-lives have passed before the substance decays to 8.3? Now we can do this one of 2 ways. The first way is we just taken the 132.8 and divide by 2 a bunch of times. And you don't even have to use an exponential. However, the other way to do it is 8.3 is equal to the initial 132.8 E raised to the negative 0.33895 times T, and solving for T in our usual way, which means I'm going to divide both sides by 132 and take the natural log. So I have the natural log of 8.3 divided by 132.8 is equal to negative 0.33895 T. So I'm going to put that in my calculator. I'm going to do the natural log of 8.3 divided by 132.8. And I'm going to take that answer, which was a negative 2.77, and divide by my half-life rate that I got. And I end up with T is equal to 8.18 minutes. And you're like, but Professor Adams, I was following along and I got 4. I took 132 divided by 2 4 times and I got 8.3. Well, yeah, that's 4 half-lives at 2.045 minutes, which still gives you 8.18 minutes. So sure, you don't have to use the exponential equation. You just got to remember that you have 4 half-life cycles, and each cycle is 2.0545 minutes. Okay, so let's take a look at the next one. A tumor is injected with 0.5 grams of iodine-125, which has a decay rate of 1.15% per day. Write the exponential model representing the amount of iodine remaining in the tumor after T days. Then use a formula to round the amount of iodine that would remain in the tumor after 60 days. Round to the nearest gram. So we're going to use the formula. A of T, the amount at time T, is equal to P naught, E raised to the KT or RT. Doesn't matter which one you like. So A of T is equal to, I start out with 0.5 grams. E raised to, I'm going to turn this into its equivalent decimal, and it's a negative because we're in decay, so negative 0.0, I don't know what that was. try this again, 0.0115 times t. So there's my equation. If I'd like to know how much is there after 60 days, I'm going to do a of 60, which is 0.5 e raised to the negative 0.0115 times 60. And I end up with approximately 0.3 grams. And that's it for that one. Okay, so following the birth of a grandchild, a grandparent wants to make an initial investment P naught so that it's going to grow to $50,000 for the child's education at the age of 18. Interest is compounded continuously at 5.3. What should the initial amount be? So we know what the ending amount is. That's the A of t. This is A at some time t. And in fact, we know at time t it is 18 years. So let me rewrite this as A of 18 is equal to that $50,000. So $50,000, need one more zero, is equal to P naught, that's what we're searching for, e raised to the 0.053 as a decimal times t. So we happen to know what t is. T is 18 years. So I'm going to put in 18. So all I have to do now is get out my calculator and do the 50,000, divide it by e raised to the 0.053 times 18. And I get an initial amount of $19,259.86 is how much they need to put into an account for that grandchild to grow to 50 grand by the time that they turn 18. Now let's take a look at our next example. A biologist records a count of 360 bacteria present after 5 minutes and 1,000 bacteria present after 20 minutes. This is just like the one that we started out with on the warm-up questions. With the warm-up questions, we had two ordered pairs. So my first ordered pair is after 5 minutes, because 5 is my independent, there's 360 bacteria. And then after 20 minutes, so here's my second ordered pair. After 20 minutes, I had 1,000 bacteria. So the first thing I have to do is find the equation where I have A of t is equal to P naught E raised to the RT. Now, if you remember, this is a heck of a lot like the ones where we had the B and the A. So my first equation is going to be 360 is equal to P naught E raised to the 5R. Now my second equation is going to be 1,000 is equal to P naught E raised to the 20R. So I'm going to solve for P naught because it's the only one that doesn't have a power on it. So I'm going to solve for P naught, and I'm going to have 360 divided by, get rid of this, divided by E to the 5R is equal to P naught. Now I'm going to put that in here where I see the P naught. So I have 1,000 is equal to 360 divided by E to the 5R times E to the 20R. So this ends up becoming 1,000 is equal to 360. Using my rules of exponents, this becomes 15R, e to the 15R. So now what I'm going to do is I'm going to divide both sides by the 360 and then take the natural log of both sides. So I'll end up with a natural log of 1,000 divided by 360 is equal to 15R. And I divide both sides by 15 and I end up with 0.06811. And they said how many decimal places? 6 1, 2, 3, 4, 5, and I guess the last digit would be a 0, is equal to my growth rate. So my equation then is, oh, I need to find my P naught. I'm going to put that back in here. So I'm going to have 360 divided by E, 5 multiplied by 0.068110. And this is going to give me my initial bacteria. And then I can finally build my equation. So 360 divided by E raised to the 5 times that number I just got. And I have P naught, and I always round up, 257 is my initial count of bacteria. Now I'm ready to build my equation. So my A of T, or P of T, whatever variable you're using, it doesn't really matter. 257E raised to the 0.0.0681110T. So there is my equation. Then it asks me how long is it going to take to double? Well, remember, I need to find my doubling time, my capital T. This is going to be equal to the natural log of 2 divided by my rate, and my rate is 0.068110. So I'm going to put that in my calculator. So the natural log of 2 divided by that 0.068112, and my time is 10 minutes. 10.2 minutes. So not very long before that bacteria takes over. Okay, so Fibonacci numbers were named after Leonardo of Pisa, also known as Fibonacci, and was used to determine the population of rabbits in ideal conditions. So assuming you have a pair of breeding rabbits, one male and one female born, after 1 month, the rabbits mate. That's how long it takes. 1 month after they're born, they can mate. At the end of the 3rd month, there are now 2 pairs of breeding rabbits. The initial pair produced a breeding pair. This continues and can be described in the first Fibonacci numbers. 1 pair after 1 month when they were born, and then 1 pair when they had them. Then we have 2, then 5, then etc. So after 20 months, we have 6,765 rabbits. How many rabbits would you have if you had 100 pairs? What would this do to your rabbits? How many rabbits would you have if you started with 100 pairs of breeding rabbits after 6 months and 12 months? Well, using this formula, 1 month, 2 months, 3 months, 4 months, 5 months, 6 months, if I start out with 1 and I have 8, then if I start out with 100, after 6 months, I'm going to have 800 pairs. After 12 months, it would be 144 times 100. So I'll have 14,440 rabbits if I started out with 100. Now, under ideal conditions, a rabbit population can actually be modeled with an exponential function, a growth rate of 19% a month. That's actually quite a bit. So what would be my equation? So I would have P of T, or A of T if you want, is equal to 100 rabbits, E raised to the 0.19 times T. And what is it going to look like when I have in the 6 months and when I have the 12 months? So I'm going to do P of 6 is equal to 100 E raised to the 0.19 times 6. Similarly, I have P of 12 is going to be 100 E raised to the 12 times the 0.19. And I'm going to put these in my calculator. And I'm going to get, let me see, 100 E raised to the 0.19 times 6. And I'm going to get 313 pairs of breeding rabbits. And then if I do it after 12 months, so e raised to the 12 times 0.19. I'm going to get, so rounding up of course, I'm going to get 978 breeding pairs. So the doubling time is about every 3 or 3.5, 4 months approximately. The Fibonacci is going to grow much faster. You can tell by comparing these, it's going to grow much faster. So theoretically, we're going to have a lot of rabbits. Is the population rabbits of an exponential function close to the population of rabbits from the Fibonacci? Not really. So Fibonacci is like the most ideal conditions, the best food, there's no predators, there's nothing else going on, and all they can do is just breed like rabbits because they're rabbits. Realistically, though, it's usually going to be an exponential growth. It's more realistic. So, yes, Fibonacci can model your rabbits if everything is ideal, the ideal food, the ideal space, no predators, the ideal water, all the resources are ideal. Yes, you're going to get that many rabbits. However, realistically, that's not going to happen. And, oh, the doubling time. I said it was around 3 and 4. Let's actually do that. So t is equal to the natural log of 2 divided by that 0.19. And I ended up with, in my calculator, about 3.6 months. So between 3 and 4 is what I said. So yeah, it's not a bad guess. All right, that's it for this video.